Imagine gazing up at the night sky on a crisp, clear evening. Among the tapestry of stars, one planet stands out, a shimmering, rust-colored beacon that has captivated the imaginations of humanity for millennia. This is Mars, the so-called Red Planet, a world so striking that ancient civilizations named it after their gods of war and made it the centerpiece of myths, legends, and dreams of conquest. But beyond its evocative hue lies a story that is not just about color, but about the very forces that have shaped planets, sparked scientific revolutions, and may one day determine the fate of our species. Today, we embark on a journey that goes deep beneath the surface of Mars, exploring why it is red, what that color really means, and how unraveling its mysteries could transform our understanding of life, death, and our own cosmic future. For thousands upon thousands of years, Mars has been a source of wonder, curiosity, and speculation. Ancient astronomers from Babylonia to China tracked its movements across the heavens, noting how it sometimes seemed to wander backwards, an optical illusion known as retrograde motion. Its reddish glow set it apart from the other wandering stars, or planets. For the Romans, the color spoke of blood and battle, so they named the planet after Mars, their formidable god of war. In Greek mythology, Mars was known as Ares, and in Hindu tradition, the planet is called Mangala, associated with strength and vitality. Even in ancient Egypt, Mars was linked to the god Horus, symbolizing the eternal struggle between order and chaos. These ancient connections highlight how deeply Mars is woven into the fabric of human culture. But what is the true source of this enigmatic color? To answer that, we must turn to science. Mars glows red because its surface is covered by a layer of iron oxide, what we know on Earth as rust. This is the same compound that gives old bridges, abandoned cars, and even your own blood that familiar reddish hue. In your bloodstream, iron and oxygen bond together in a molecule called hemoglobin, carrying life-giving oxygen through your body. On Mars, iron in the rocks and dust combines with oxygen in the thin atmosphere, coating the landscape in rust over billions of years. This seemingly simple process is actually the result of a dynamic planetary history, one that reveals as much about the planet's past as it does about its present appearance. But the story is more nuanced than a single color. Jasmine, a thoughtful 14-year-old from Washington State, posed a deceptively simple question. Is Mars really as red as people say? The answer, as scientists are discovering with every new mission, is far more complex and fascinating than most people realize. The Red Planet is a world of subtlety and variety, a place where rusty browns, golden tans, shimmering white polar caps, and dark volcanic plains blend together in an alien mosaic. The earliest color images transmitted by the Viking landers in the year 1976 showed a world blanketed in orange-red dust, but with hints of ochre and brown. Later, the Hubble Space Telescope and the Mars rovers, Spirit, Opportunity, Curiosity, and now Perseverance, revealed a landscape of astonishing diversity. From the sunlit slopes of Mount Sharp to the shadowy depths of Valles Marineris, no two regions are exactly alike. Mars's color palette is shaped by more than just iron oxide. The planet's polar caps, for example, shine brilliant white in the Martian winter, composed of both water ice and a layer of frozen carbon dioxide, what we call dry ice. These ice caps grow and shrink dramatically with the changing seasons, as the dry ice sublimates in sunlight and refreezes in darkness. In the mid-latitudes, tan and brown plains stretch for hundreds of kilometers, dotted with ancient riverbeds, impact craters, and vast dunes sculpted by relentless winds. Near the equator, dark streaks mark the slopes of extinct volcanoes, hinting at a violent geological past. The interplay of these colors is not just beautiful, it is a record of the processes that have shaped Mars over billions of years. But what exactly determines what we see? The answer is, in part, the way light interacts with the Martian surface and atmosphere. When sunlight strikes the planet, different minerals absorb and reflect light in unique ways. Iron oxide, especially in its finely powdered form, reflects red and orange wavelengths, while other minerals like basalt or olivine reflect darker shades. Scientists use not only visible light cameras, but also specialized instruments that detect infrared and ultraviolet light, wavelengths invisible to the human eye. These tools, aboard spacecraft like NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express, allow us to map variations in mineralogy with extraordinary precision. But the real breakthrough in our understanding came with the identification of a particular mineral, ferrihydrite. According to planetary scientist Adomas Valentinus at Brown University, our understanding of why Mars is red has been transformed by the discovery that ferrihydrite, rather than just generic iron oxide, plays a key role in coloring the Martian dust. Ferrihydrite forms in the presence of water, suggesting that Mars's distinctive hue is not just a product of chemical weathering, but a lingering echo of ancient wet environments. Brian E. Horgan of Purdue University adds, pinpointing the specific iron oxide variety is crucial for deciphering the processes and timing of Martian dust formation. In other words, by analyzing the color and chemistry of Martian soil, we are reading a planetary diary written over eons. But Mars's color is more than skin deep. It is a window into the planet's tumultuous history, a story of volcanoes, floods, and cataclysmic change. Billions of years ago, Mars boasted a global magnetic field, roaring volcanoes, and rivers of liquid water that carved vast canyons and filled ancient lakes. The sedimentary rocks explored by NASA's Perseverance rover in Jezero crater reveal layers upon layers of clay, carbonate, and hydrated silica, minerals that form in the presence of water and can trap microscopic traces of past life. In fact, hydrated silica is famous on Earth for preserving ancient microbial fossils, raising tantalizing hopes that Mars rocks may hold similar secrets. The search for life on Mars has been a central quest for decades. The Viking landers in the 1970s performed the first experiments to detect life, sparking controversy and debate when their results proved inconclusive. More recently, NASA's Curiosity rover detected mysterious spikes of methane in Gale crater, a discovery that has electrified the scientific community. Methane is a molecule that, on Earth, is often produced by living organisms. While some methane on Mars could be generated by chemical reactions between rocks and water, the possibility remains that microbes lurking in the Martian subsurface may be hard at work even today. As Sushila Treya of the University of Michigan explains, Curiosity's methane detections hint at extant microbial processes thriving beneath the Martian surface. If this is true, it would mean that Mars is not just a dead planet, but a living world, one whose most important inhabitants may be hidden from view. But the path to understanding is not without obstacles. Mars is a planet full of puzzles, and each answer seems to raise new questions. For instance, why did Mars lose its magnetic field? Around 4 billion years ago, Mars had a magnetic dynamo, much like Earth's, which shielded the planet from solar wind and helped retain a thick atmosphere. Then, for reasons still debated, this dynamo shut down. Without its protective bubble, Mars's atmosphere was gradually stripped away by the relentless bombardment of charged particles from the Sun. NASA's MAVEN spacecraft has traced how this solar wind eroded the Martian air, altering the climate and making the surface inhospitable to most forms of life as we know it. The loss of atmosphere led to the freezing of surface water, the collapse of the greenhouse effect, and the transformation of Mars into the dry, cold desert we see today. This transition was punctuated by titanic events. Cataclysmic megafloods triggered by volcanic heating or asteroid impacts once scoured the Martian surface, carving out channels hundreds of kilometers long and reshaping entire regions in a matter of days. Volcanic eruptions continued until only a few million years ago, a blink of an eye in geological time, blanketing the landscape with fresh lava and ash. The interplay of water, fire, and ice left chemical fingerprints in the rocks, preserved for eons under the protective coating of iron-rich dust. Each new mineral detected by our robotic explorers adds another piece to this intricate puzzle. As we continue to probe Mars' mysteries, the stakes are rising. Humanity is now on the cusp of a new era, one defined by the ambition to send people to Mars, establish permanent outposts, and perhaps even build thriving colonies. The color of Mars is not just a scientific curiosity, it is an urgent practical question. The same iron oxide dust that paints the planet red can be both a blessing and a curse. On the one hand, this dust is abundant and could serve as a raw material for construction, radiation shielding, and even the extraction of oxygen for life support. On the other hand, the dust is laced with perchlorate salts, chemicals that, while potentially useful for supporting certain types of bacteria, can be highly toxic to humans. Penelope Boston, a NASA astrobiologist, warns, perchlorates present both a challenge and an opportunity for Martian life, demanding specialized adaptations. Settlers will need to develop new technologies to manage, detoxify, or even harness these compounds if they hope to survive. The vision of Martian colonization is more than science fiction. It is a grand experiment in planetary engineering, resourcefulness, and adaptation. Imagine the first pioneers landing in habitats constructed not from expensive Earth-made materials, but from Martian regolith, the very dust and rock that gives the planet its color. Advanced techniques like sintering, 3D printing, and chemical extraction could turn this raw material into bricks, tiles, and even glass. Closed-loop life support systems will recycle air and water, while solar panels and nuclear reactors provide energy. Automated robots controlled from Earth or by artificial intelligence will scout for resources, build infrastructure, and monitor environmental hazards. The challenge is immense, but so is the potential reward. In situ resource utilization, or ISRU, will be the key to self-sufficiency. Water ice found in the subsurface and at the poles can be extracted for drinking, agriculture, and the production of hydrogen fuel. The extraction of oxygen from iron oxides, using techniques pioneered on Perseverance, could provide breathable air and propellant for rockets. Experts like Robert Zubrin of the Mars Society argue that Martian colonization is paramount for averting a dystopian future and ensuring humanity's long-term survival. If we succeed, Mars could become a springboard for the exploration of the entire solar system, fueling missions to the asteroid belt, the moons of Jupiter and Saturn, and perhaps even beyond. But with this opportunity comes profound responsibility. The risk of contaminating Mars with Earth microbes is not hypothetical. It is a real and present danger. Forward contamination could obscure signs of native life, disrupt fragile ecosystems, or trigger unintended consequences. International protocols, developed by planetary protection offices at agencies like NASA and the European Space Agency, set strict guidelines for sterilizing spacecraft and handling Martian samples. The upcoming Mars Sample Return mission, a partnership between NASA and ESA, will bring pristine soil and rock back to Earth for the first time in history. Colin Wilson, project scientist at the European Space Agency, underscores the importance. Earthbound analysis of Martian samples will precisely quantify ferrihydrite content, revolutionizing our grasp of Martian water history. The data gleaned from these samples could settle long-standing debates about the planet's habitability and provide critical insights for future explorers. At the same time, the psychological and ethical challenges of Martian settlement loom large. Astronauts and settlers will face isolation, confinement, and the strain of operating in an environment that is, at every turn, trying to kill them. The distance from Earth, ranging from 56 million to over 400 million kilometers, means that help is never just a phone call away. Communication delays of up to 24 minutes each way will force crews to make autonomous decisions and rely on robust artificial intelligence systems. Maintaining mental health, fostering cooperation, and resolving conflicts will be as vital as any technological breakthrough. These challenges have not deterred international collaboration. The race to Mars is not a zero-sum game, but a shared quest that has already brought together scientists and engineers from dozens of countries. The European Space Agency, Russia's Roscosmos, NASA, China's CNSA, India's ISRO, and private companies like SpaceX and Blue Origin are all investing heavily in missions to study, orbit, and eventually land on the Red Planet. Each brings unique capabilities, perspectives, and ambitions. The ExoMars mission, a collaboration between Europe and Russia, is searching for biosignatures with a drill capable of reaching 2 meters below the surface. NASA's Perseverance rover, equipped with the MOXIE experiment, is testing the production of oxygen from the Martian atmosphere, a crucial step toward independence from Earth. The Chinese Tianwen-1 mission, with its own rover and orbiter, is mapping geology and searching for water ice. As new data pours in, our conception of Mars is evolving rapidly. Recent discoveries have upended old assumptions and opened new avenues of inquiry. For example, Martian meteorites found on Earth contain organic molecules, complex carbon compounds that are the building blocks of life. While these molecules can form through non-biological processes, their presence strengthens the argument that Mars was, and perhaps still is, a habitable world. The analysis of isotopes in Martian rocks has revealed that the planet's core is smaller and denser than previously thought, with implications for its magnetic history and volcanic activity. RIMFAX, the ground-penetrating radar on Perseverance, is mapping the subsurface layers of Jezero crater, revealing ancient river deltas and possible aquifers. The consequences of our actions on Mars will reverberate far beyond the red planet. The technologies developed for survival, radiation shielding, water recycling, closed-loop agriculture, and autonomous robotics will have applications here on Earth, from disaster relief to sustainable cities. The lessons we learn about planetary change, climate resilience, and the fragility of ecosystems could help us safeguard our own world against looming threats. As climate change accelerates and natural resources grow scarcer, Mars serves as both a warning and an inspiration, a reminder that planetary environments are precious and precarious. Yet there is also hope. The very act of reaching for Mars brings out the best in humanity: creativity, courage, and the willingness to work together across borders and generations. The journey will not be easy. There will be setbacks, failures, and unexpected challenges. But the rewards, a deeper understanding of our place in the universe, new technologies, and perhaps even proof that we are not alone, are worth the risk. And so, the saga of Mars remains unwritten. Will humanity's first permanent foothold spark a golden age of discovery, or will we stumble into consequences we never anticipated? The answer depends on our ability to balance ambition with caution, exploration with stewardship, and curiosity with respect for the unknown. As we stand at the threshold of a new era, let us remember that Mars is more than just a red dot in the sky. It is a mirror reflecting our hopes, fears, and dreams, a place where the color of dust tells a story billions of years in the making. And here's one final, little-known fact to leave you pondering. Scientists have discovered hydrated silica on Mars, a mineral renowned on Earth for preserving ancient life. If Martian life ever existed, or if it still clings to existence somewhere in the subsurface, its fossilized remains may be locked within those very red rocks, waiting for us to find them. The next sample we analyze could rewrite the history of life in the solar system. So, what do you think? Are we ready for the risks and rewards of turning Mars from a symbol of war into a beacon of hope? Could the red planet, once an emblem of blood and conflict, become the cornerstone of a peaceful interplanetary civilization? Let us know your thoughts in the comments below. Share your wildest Mars predictions, your most daring hopes for humanity's future among the stars, and don't forget to subscribe for more deep dives into the secrets of our universe. The next era of exploration is about to begin, and you could be among the first to witness it.